students, I want to finish up this example, this example problem from class today and show you the other problems that we were scheduled to do, but could not because of the evacuation. So remember what we just did was we sketched the two curves, and since it says we want to sketch the region bounded by these curves, what we're talking about is the area between them, and they only gave us an upper limit, x equals 3, so what we had to do is we had to manually find the lower limit, which is the point of intersection between the two curves. And so we have negative 1.37 being our lower limit, positive 3 being our upper limit. And the first thing I want to do is write this problem in integral notation. So I'm going to say, using the rule that we copied down in class, we're going to take the integral from negative 1.37 to 3 of the absolute value of the difference of the functions. Okay, so the absolute value of square root of x plus 2 minus the other function, 1 over 2x plus 4, dx. Okay? And so, what we can do is we can put this in our calculator. Since we already have these two functions in our calculator, we can make our lives a little bit easier by putting the absolute value of the difference of these two functions as y3. So remember, absolute value is, in our math option, right arrow to numbers. Option 1 is absolute value. And remember that the order of subtraction does not actually matter here, because the absolute value takes care of that. And so we want to put our y variables, y2 minus y1 or y1 minus y2. Doesn't matter, so go to vars, right arrow to y vars, enter y2 minus, same thing, vars, y vars, y1. And what I want to do at this point is I want to make sure that I'm only graphing this third option, y3. So I'm going to press enter and turn off the two graphs, the two other graphs, so that when I calculate my integral, it's only giving me the integral of the combined functions, right? And so I can zoom 6 this. All right, look, we've got a positive function only. This is a combination of the two functions. This is the difference, the absolute value of the difference between the two functions. And now I can go back to second, calc, and do the integral. Option 7, lower limit negative 1.37, enter. Upper limit is 3, enter. And our integral, which represents the area between the two curves, is 6 point, oh, I can't even read that. 6 point something. 6.08. All right, and so this is one way of doing this problem. All right, so now I want to show you how to do another one using a slightly different calculator method. We are going to find the area of the region bounded by these two curves, and they've given us a lower and upper limit. So the first thing you should do is just make a quick sketch of the graph that we're looking at. You can do that using your calculator or just using what you know about trig functions. I'm going to make one of these a sine cosine. I'll make that in red, and the cosine, I'll make that in blue. So we know these are our two graphs. We're looking at the interval from 0 to 2 pi. So these are our two vertical lines, our lower and upper limits of integration. And remember, we're looking at just the area between the two curves. So this area, and this area. Okay, so once again, let's go to our calculator. And what we can do here is have our sine of x in one, our cosine of x in the other, y equals. You can graph it if you want. We already know what the graph looks like. Zoom 6, it's that same graph we just sketched. And actually, when you're sketching trig functions, Make sure your mode is in radians, and instead of zoom 6, you should go to zoom 7. That's zoom trig. Okay, so it'll give you a nicer window to view the trig functions on. All right, now instead of going to our y equals, and finding the integral on the graph, thank you, Robin Mills, for showing us this, we can actually just go to math, and option 9 is an integral. All right, so we're going to choose option 9 here. All right, there, enter. And we know our lower and upper limits, right, from 0 to 2 pi. And actually, before we do this, I'd like for us to write this in integral notation. From 0 to 2 pi, finding the area between two curves, what we're going to do is take the absolute value of the difference between the two functions. So the absolute value of the difference between sine and cosine x dx. Okay? And so on our calculator, from 0 to 2 pi of, and here in this parentheses, we can type out sine x minus cosine x, or rather the absolute value of sine x minus cosine x, or we can again go to our y bars since we already had it typed in there. So I'll just use the y bars. But first I'm going to put my absolute value symbol, math, right arrow, option 1, apps, and then I'm going to put bars, right arrow to y bars, and I want to do my y1, which I think was my sine x, minus bars, my y2, which was the cosine x. And here, you need to put the variable that you're working with. So since we had x in our equation, we should have dx at the end of this integral. And press enter. And it's going to take a minute. His little brain is working. But it's going to show us the value. The value of that integral is 5.66 approximately. All right. So we can use a couple of different methods on our calculator to find these values. All right, there is one last example I want to show second period that I didn't get to. I did show the first period class this. And it is the area between a curve and the y-axis. Now, if you recall, what we've been doing with integrals so far is calculating the area between some curve, say for example, a sine curve or a cosine curve, and the x-axis between two vertical lines. So we've got some value x equals a here, some vertical line x equals b here, and the integral from lower limit a to upper limit b of f of x dx will give us this area bounded between the x-axis, the curve, and these two vertical lines, right? That's what the area is. It's that integral. Now, that was bounded by the x-axis and two vertical lines. Now what we're going to be looking at is the area bounded by the y-axis and a curve and two horizontal lines. So let's say we've got some curve. Now we are looking for the area bound between some value, some horizontal line, y equals a, lower limit, some horizontal line, y equals b, upper limit, and the y-axis and the curve. This area is what we are going to be calculating now. Notice how this is different. We are bounding between the curve, the y-axis, and two horizontal lines. Now the rule for doing this, pause the video, write this down. the area of the region bounded by the curve x equals h of y. This means we are going to have to rearrange our equation to make y the subject. Isolate x, make y the subject. Y equals A and y equals B are horizontal lines. Note that down. Y equals is a horizontal line. Y equals a constant. Where h is continuous for all y, we're always given continuous functions, is given by this. The integral from a to b of the absolute value, because whenever we're talking about area, we got to deal with the absolute value of the integral. This area is always positive, the absolute value of the function. So let's look at one example utilizing this. Find the area of the region bounded by the curve y equals x squared and the y-axis, where x is in the set of numbers from -2 to 0. Okay, so first let's make a sketch. Let's make a sketch. We know what this graph looks like. This is a parent quadratic function. All right. Now notice here, we are dealing with the y-axis. All right, so that's the first hint that you need to look at the rule you just noted down. All right, so what I see here is some x values, but I've not been given the y values. Remember, when we're bounding the area between a curve and the y-axis, we also need two horizontal lines. So let's find out what those corresponding horizontal lines are. When x equals -2, based on the function y equals x squared, so y equals 4. That is one of our bounds. And when x equals 0, y equals 0 squared, so y equals 0 is our other bound. Okay, and so that corresponds with this point right here, 0, 0, and -2, 4. So what do we have here? Well, oops, we are looking at the area bounded by the curve, the y-axis, and these two horizontal lines. We're looking at the left side of the curve. Why? Because x equals -2 is what they were referring to. -2 and 0 is right here. So here's the one simple algebraic thing that we have to do whenever we're doing this, and then we'll leave the rest to our calculator. We need to find x in terms of y. All right, so if y equals x squared, we simply need to make y our subject. We're going to take the square root of both sides to isolate x. So x equals a positive and negative square root of y. Since we're dealing with the left side of the curve, we're just going to look at the negative square root of y, and this is the function that goes into our calculator. So first, let's write the integral in terms of y. Our area is going to equal the integral with lower limit of our first lower horizontal line, y equals 0. Upper limit is our second horizontal line, y equals 4. Sorry, I didn't mark that on this diagram. This is a 4. All right. Of this absolute value of negative square root of y, no longer dx. Now, since our variable is y, it is dy. And let's put that into our calculator. So I can show you the same calculator move we did last time. We're going to go to math, the number 9, and instead of putting this into our y equals, because we're dealing with y variables instead of x variables, we are going to put this just on the calculation screen. 0 to 4, absolute value of negative second square root of, and if you want to put y, you can put y into your calculator now. You just have to press alpha and look for where it has y above the number. Square root of y, just have to make sure that you also write dy. All right? Those two variables have to match, and it'll calculate for us. Ta-da, 5.33. That's it. Please practice exercise 11H.